All right. So I showed this last week. I want to show it again because we're going to talk about specifically for proportions and start to get some formulas. That's what we're going to look at and do today. And so the idea is that, let's say we're taking a sample of size 25, and we're keeping track of the amount of oranges. Let's make it more interesting and make it 0.4 instead of 0.5, just so it looks a little bit different. So, how many, you should know the answer to this, how many of the candy should I expect to be orange? How would I do the calculation? 25 times 0.4. That's expected value of a binomial distribution, which is what this is. Right? I'm taking a set amount. There's a set proportion of them that are orange, and the variable I'm keeping track of is how many of them are orange. That's why I showed this, is that this would have a binomial distribution. My expected value is 10. That would be 2/5 of 25. Oh, this sample, though, we got 13. Interesting. And then we could start to get a distribution. If I took a whole bunch of samples, instead of one sample, let's take 100 samples. I could keep taking samples of 25. And the more samples I take, the more this is going to start to look like a normal curve. The more it's going to start to look like a normal distribution. Now, if you remember, in a binomial distribution, we're going to use all these formulas. The mean was n times p, and the standard deviation was the square root of n times p times 1 minus p. That was our distribution. That means standard deviation. If we're getting a sampling distribution of proportions, so I want to know the mean of the distribution for p hat of all the different samples I could take. It should be centered at the proportion. All we're doing, the only difference between my number of candies distribution and my proportion of candies distribution is that instead of looking at the number, we're doing the proportion. And so here's what that would look like. Notice how close, now that we're taking 200 different samples, 200 different samples now, notice how close this is looking to a normal curve. Guess where it's centered? 0.4. I hope so. But what we're going to do is we're going to take these binomial formulas, and all we're going to do is we're going to divide them by n. We're going to say instead of how many in the sample, we're going to take it as a percentage. And so we're going to divide all these by, in this case, 25. Oh, hey, when I divide all the numbers by 25, what happens to the mean? It gets divided by 25. What happens to standard deviation? Also gets divided by 25. That's what multiplying and dividing by the same number will do. And so let's divide it by our sample size. Standard deviation take that square root of NPQ, that standard deviation formula, and we're going to divide it by our sample size. If we put it all underneath the square root, then n is the square root of n squared. And so we get these n's canceling. That's a bad cue. Don't worry about it. So here is our formulas. Here are our formulas for the distribution for proportions. Now, one thing we talked about very briefly in chapter 6 that we're going to talk about again is some conditions. I said it starts to look really close to a normal distribution, but that has a couple of caveats. Again, it's looking close to it, not exact, and it only does that when I do enough samples, when I have enough data points, and when I have a large enough collection. Right? If I just take a sample of one candy, then there are only two possibilities that I can get. Will you get a center of 0.5? Yes, but all the samples will be either one of the candies or zero of the candies. So that's not going to look like a normal distribution. In other words, I need to be sampling enough. How much is enough? Well, we're going to have a kind of component here. Remember, p hat for our sample. And another thing we talked about earlier on in the chapter is that as our sample size gets bigger, as we sample more people, it starts to get a smaller spread. That's something we talked about earlier on in the chapter. And you can see that in the formula. If I make n bigger, then the number at the bottom gets bigger, the denominator gets bigger, which is going to make the overall number smaller. So larger value of n means smaller value of standard deviation. And you'll see that in the formula in the next section as well. Shape is going to start to look like a normal distribution. Center, it should be centered at the proportion. I hope. And then our spread depends on our sample size. And so we take these formulas for binomial, divide them by n, and these are our formulas for binomial. And I said we need to sample a large enough size. This is going to be the condition we need to check to make sure we can actually use a normal distribution. And that it will actually start to look like a normal distribution, which is that the expected number of successes and failures need to be at least 10. What you may do for the formula is that n times p and n times 1 minus p have to both be at least 10. Pay attention to that close enough to normal, because in the next section, that condition is going to change. Right now, we're looking at proportions. And if you're looking at proportions, then it's n times p and n times 1 minus p. So in the example that we did with the candies, our expected number of successes was how many? Out of the 25, we expected how many of them to be orange? We expected 10 of them. How did we get that? We got 25 times 0.4. That's the n times p. And then that left 15 of them that we expected to not be orange. N times 1 minus p. So 25 times 0.6. So in that case, we can safely say that we are looking at an approximately normal distribution. So that's something we need to check. All right. So those are the formulas that we're going to use in our normal calculation here. Democrats, so I'm using blue. I'm so clever. All right. One of these is P, and one of these is talking about P hat. So one of them's talking about P, one of them's talking about P hat. You need to figure out which one's which. How do you know that the 30 is talking about P hat? So the 43% of the registered voters. So this is of population. This is 30% in a sample. So let's take a look. This is P. And then we want to know about less than 30% for P hat. So we are trying to find the probability that P hat is less than 0.3. That is what we're looking for. Hold on before we do any more calculations. Normal? We're going to check n times P and n times 1 minus P. What's our n? 50 is our sample size. So n times P is 50 times, we already decided P was 0.43. Which is 21.5. N times 1 minus P is going to be 50 times, what will 1 minus P be? That leaves what percentage to not be Democrats? 57. Someone double check me on those. Those seem right to me. The key part is that they're both at least 10. So we can use a normal distribution. Well, that's great news for us. Mean. It's just P. Standard deviation, this is where we need a formula. Square root of PQ over N. Square root of P, which is 0.43, times 1 minus P, which is 0.57, over N, which is 50. That one I can't do in my head. Someone needs to tell me what that is. All right, we'll go with 0.07 for the sake of drawing a normal curve. Always suggest drawing a picture so you can get a sense of the distribution and the area that you're shading here. We're centered at 0.43. And then we need to take 0.47. I always draw 2 standard deviations on either side. 0.5, 0.57, 0.36, 0.29. We want 0.3. We want to know about 0.3. We want to know about everything to the left. Remember, the idea here of what this curve is, this curve is trying to talk about what percentage we could get for every sample of 50. What percentage of the samples we would get would be Democrat. So the question that we're asking here is something like this. I took a sample and I got 30% of them being Democrats. What we will start to talk about is saying that might mean one of two things. Number one, I just took a sample that happened to have a low amount of Democrats in it. And that just happened by chance. I just had an unusually low value. Or number two, the percentage of Democrats in Arizona has changed. And looks like has gotten lower. And it wasn't just that we took a bad sample, it's that this distribution looks different than it used to. So those are the two possibilities. Either we just happen to get a low sample, or the probabilities actually changed. The first one, we can actually calculate. We actually know how to do that calculation. So we're going to go through and do that calculation. So that's what we're doing right now, is saying what are the chances that we just took a sample that happened to be that low. If you prefer z-scores, then the z-score formula that you're using is the value is 0.3 minus the mean is 0.43 over the standard deviation is 0.07. That z is less than this value. So either way you want to do the normal CDF. Either with the z-score value or with or just putting in the values in the mean and standard deviation. Either way, your lowers should be really low. Your uppers should go all the way up to this end point. And then mean and standard deviation. And let me know what we get. I have an estimate. So if you're sounding way off from my estimate, then while I'm about to get that value out, have a homework assignment while I wait for people to type in their calculators. What do we get? 0.0316. Agree over here? I'll come back over here in just a minute. I want to finish up this. What we're going to start with tomorrow is this example. I want you to try it before class tomorrow. So you guys here got a few minutes to give this a try. And we're going to start class tomorrow. I'm going to put the answer up there and see what questions we have. And then I'm going to move on. So figure out what's your population. So which one is P and which one where are we talking about P hat? What values are we looking for P hat? And then, once we know what the population is, that will give us the calculations for mean and standard deviation. We also want to check n times P and n times 1 minus P. Then get your normal curve. So that's what I'll start class with tomorrow, is showing that answer.